Okay, I'm going to start introducing our first speaker. We are very fortunate to have Professor Amit Bhasin from University of Texas at Austin. Dr. Bhasin used to be a young and upcoming researcher in transportation materials area a few years back. Now he has fully established himself. He actually is the director of the Transportation Research Center at UT Austin, which is a very well-known and long-running large center for many, many decades. His primary research interest is in pavement materials, particularly on asphalt concrete. He has received many awards. I'm not going to read the whole thing. It's going to take a few minutes if I do that. But he got the NS Korea, which is very uncommon for transportation materials people. I suspect in the history of NS Korea Awards, there may be a handful in the last few decades. And he is a recipient of that award. Without further ado, I would like to introduce my old friend, Professor Amit Bhasin, to talk about a big topic that I have immense interest in myself. Instead of making small steps, we need to take giant leaps in pavement engineering and materials. Without further ado.
Thank you so much. Thank you very much, Kevin, for the kind introduction, and Professor Zaman for organizing this and inviting me here. It's been wonderful, and it's such a pleasure to be out here in person. So this is after TRB. This is the 2020. This is the first time I got on a plane. So thanks for breaking the ice on this. Thank you so much. This is the topic. But before I get started, let me just give 3 disclaimers. The first one is that I'm talking a little bit about big steps and transformative research or disruptive ideas, whatever adjective you want to call it, or the buzzword you want to introduce there. But that does not mean that what we do is not important. What I call here as incremental research or need-driven research or problem-driven research, I don't mean to imply that that is not important. It's very important and critical, but this is just an opportunity to pause and rethink what we're doing. The second disclaimer is that most of the examples and ideas that I'm presenting here are from the asphalt, pavements, and materials area, because that just happens to be the area that I've been working with for past many years. But I hope, and I know the audience here, and y'all are from many different aspects of transportation engineering, so I hope you draw some ideas or analogies from this that may or may not relate at different levels to what you all do in your fields of specialization. The third disclaimer is that since this is right after lunch, I'm sticking to very high-level ideas with no equations or mathematical modeling involved whatsoever, and so forgive me for keeping it such a high level. All right, so as is customary, got to have an outline, so that's the outline. So let me talk about where we are in pavement research. This is sort of, I've been thinking about this and having conversations with colleagues in my area of research from around the world really for the past few years, and increasingly more so in the past few months or so. Perhaps this COVID and pausing travel has given us an opportunity to stop, rethink where we are in terms of research. So, just out of curiosity and looking at that, I went to Web of Science and looked at, okay, as academics, people, what do we produce? One of the things is, in terms of knowledge creation, one of the ways you can track knowledge creation is through publication. So I went to the Web of Science, and this is the data from Web of Science, and looked at how many papers have we published. And these numbers are it's just from Web of Science indexed journals. So it does not include numerous reports and articles and conference proceedings and other stuff These are just a limited pool of indexed journals, and it is just based on keywords of asphalt and flexible pavement. So it does not even look at basis, Dave Mishra, so does not look at pavement foundations or other areas of transportation, just asphalt materials and pavements, right? So if you look at that, that number is like from 1990s to 2020, that growth has been enormous in terms of knowledge creation. But then we came back and thought, okay, how have we changed the business, the way we do things? What were the biggest transformative changes? So if you go back and look at that, I thought, well, one of those big changes was the product from the Strategic Highway Research Program in the 1990s, the SuperPave mixed design system, the SuperPave asphalt binder grading system, which is now recognized internationally. Almost not every country in the world uses the SuperPave binder system or the SuperPave mixed design system, but in some shape or form they have adopted it, they follow it, they understand it. So this is how asphalt binders and mixtures are designed, or at least a framework. Even if the framework is not adopted by the states, the binder industry has really used the binder system. So that was really a transformative way. Instead of punching needles in asphalt binder, we went into mechanics, we went into rheology, we used sophisticated instruments, and I'm still amazed at how the industry came together and completely revolutionized their labs. They made huge capital investments in their labs, and they transformed the business as we did it. And that has impacted global practice. Not only that, that's impacted materials. We did not used to have polymer modified, these are highly modified materials, asphalt binders, and then the industry reacted to these specifications, and we got this whole host of polymer modified binders with extended performance characteristics and so forth. So that was amazing. The 2002 design guide, which was, okay, it was 2002, but it got released somewhere. It's still in the process of being released in some shape or form, but I remember it as a 2002 design guide when I first got introduced to it. That was, I think, another paradigm shift where we said, we're not just gonna use a number, we're gonna use mechanistic methods to design a pavement. And it was another big transformative change. In fact, looking back in the history, even before 1992, I looked at some studies from the 1970s when there was oil embargo, and Federal Highway Administration said, look, we need to get our act together. We need to figure out a way out of this in case we don't have a supply of bitumen. And so what did they do? They came up with sulfur extended asphalt. Totally new forms of asphalt that were 100% sulfur based and had nothing to do with bitumen. And there were more than 20 sections within the United States that were built using this technology. That is a stockpile of sulfur right next to a hot mix plant. We did it. Why we? I mean, I was in kindergarten, I was very small, but as a community, we did it. We took these giant leaps and we completely transformed the way we were designing materials. Now, late 70s, the embargo ended, and after the embargo ended, the cost of sulfur was 3 times the cost of asphalt binder or bitumen. It made no economic sense, so the whole technology just faded away. But it's purely economics. Today, when we stand, sulfur, the global price of sulfur is about 1/3 the cost of asphalt binder, but we haven't gone back there. It still is something out there. So what has happened then, if you look at any major paradigm shift, and I apologize, there's no literature or report on this. This was just me searching through information. Maybe I missed something that was really, really significant in this area. But if I look at that window since early 2000s to today, 2 decades, we don't have a paradigm shifting technology or the way we do business. What we do have is a lot of reactive research where we talk about problem statements, imminent issues, and we are trying to improve it. We also have a lot of technological transformations, but those would be analogous to, we do things this way, but now we're going to use technology to make it more efficient, more faster. We're not fundamentally changing the way we do things. Now, if you think about, this would be the example I was giving Professor Zaman the other day was, if you go to a library, some of you may remember before computers that you'd had to pull a cabinet and it had index cards and you would find the bookshelf where the library you wanted. So we moved from that to a computer to catalog books, but we haven't digitized the library yet. So there is a lot to be done, and that is what I thought would be something that we need to reflect on as a community, is that we have spent a lot of time and resources on reactive research. We need to think about more proactive research. That is a global number, so US alone is about 1,000 papers in Web of Science. And the other thing that it occurred to me, I just did some back of the envelope math and said, as a community from academia, that's all of us, me and my colleagues here are responsible for that. If we just do a back of the envelope math and see, how much does it cost to write a paper in terms of paying a graduate student, paying lab supplies, the money that is paid, the supervisor and all of that. And if you conservatively estimate that as $10,000 to put everything together, that number translates into roughly $10 million. So $10 million of reactive research. I mean, if I had a $10 million project today with me and my colleagues, would we want to continue to do reactive research, or would we want to do something that is paradigm changing? So that's something to think about. That's also, it also is something that we as researchers need to work with the industry, we need to work with the agencies, and think about not just problem statements, but vision statements. Think about, is this the way we're going to continue to do business in the decades to come, or are we going to try to change it into something more transformative? So, incremental versus radical advances. So let's talk about what I was talking about, reactionary research or problem statements or imminent research versus thinking more proactive. So this is sort of speed of computers from 1940 to 2020, and you'd see that in 1982 the speed of computers was measured in 10 to the power 9 flops. That flop is floating point operations per second. So you had 10 to the power 9 flops in 1982. By the way, 1982, 1 gigabyte of storage also costed you nearly $2,000, right? So move forward, we are here roughly in 2021. That's a supercomputer right there operating at nearly 10 to the power 19, 10 to the power 17, and now we touched 10 to the power 19 petaflops of floating point operations in supercomputer. The picture on the top left is something I pulled from an old AASHTO report. That was the computer that was used for the structural number and AASHTO design guide, the mechanistic MEPDG, right? So we've come from that computer to this computer here. Then I found this another picture in our archives. And, oh, by the way, just before I go there, it's not just computing speed, right? This graph that I've talked about or shown about computing speed is also applicable to sensors, the cost of sensors and sensor technology. It's also relevant to how fast and how much data we can analyze. And it's also relevant to material chemistry and advanced in material science and technology. Almost everything follows that same trajectory in terms of both the efficiency and cost. All right, so as I was going through this, I looked at another picture that came across my archives. That is Professor Frank McCullough, a colleague. He passed on a few years ago. He's done a lot of rigid pavement design. He was at UT Austin for many years. And that when I zoom in on the picture over there, he's teaching about resilient modulus, right? The change in stress divided by change in strain and so forth. And we're still using that. That's still part of the MEPDG. That's still the backbone of the pavement design system embedded deep inside in the mechanistic empirical pavement design guide, right? So what we have done the case that I'm trying to make is we've done more reactive research. We've made it much faster to compute resilient modulus. We now have nonlinear resilient modulus, more complex anisotropic resilient modulus. But the fundamentals have not changed. We've done business as we did. We've become more efficient. We've become more accurate with it, but we've not changed the fundamentals. Before I go on, there's another thing that from that slide, I've shown this in my class once or twice, but another thing I like to point out was there were no women. There were no women in that classroom over there in Frank McCullough's, and I think that's important. So a shout out to women in engineering, and let's keep moving that way. So 3 examples. So we just want to talk about what could these ideas look like. I'm no way advocating that these are the 3 ideas, but these are 3 sort of examples or short stories of journeys that we have tried to see how do we break the mold, think out of the box. So the first one is about a virtual asphalt lab. And if you think about it, this one was inspired from what's it called? Angry Birds. And I don't know if you're familiar with Angry Birds, where you throw stones at something and it's a video game on iPhone, right? So the physics engines and the gaming computers these days are so amazingly fast, and people have done amazing things with computer technology. In fact, there was one graduate student who was working on in Center for Transportation Research a few years ago, who's now, and he was doing transportation modeling, and he's now ended up with a job in Pixar animation with Walt Disney and Pixar Studios, with mathematical models to simulate things that you see, ice and snow in that, I forget the name of the movie with the snow person, sorry. But you know what I'm talking about. So simulating mathematical models for snow, water, fire, all of those things, right? It's amazing what computers can do these days. So we took those gaming engines and said, can we build a virtual lab? Can we build virtual simulation? So this is a simple compaction process that we do in a lab on a daily basis. It's in slow-mo, but it's simulated with a lot of realistic scanned aggregate particles and so forth in a virtual environment using the same principles and tools that are used in the video gaming industry, really. So now, why do this? First of all, to me, why do this? Because it's really, really cool. But that's not the reason we get paid for, right? The reason to do this is because if you're able to do these kind of experiments on a computer, imagine if I had to figure out how do I optimize aggregate gradation? How do I change aggregate gradation based on particle size? If you had to do these experiments in your lab, it would take thousands and thousands of different combinations. It would take hundreds of graduate students, millions of dollars. Would not be possible if you try to achieve something like this experimentally. But in a virtual world, you can. Doesn't mean this is the end and beginning of it. It means that, yes, you can do the first cut using computer, and then when you go to the lab, you don't have to deal with 1,000 mixes. You can deal with 20 mixes and be very efficient about it. Again, ideas to think about a little bit. That's a virtual compacted sample right there. And there's more details and so forth. I promise I won't show mathematical equations. I'll skip the text. The second short story is something that we've always questioned and talked about is cracking on asphalt pavements. That almost all asphalt engineers, cracking tends to be the favorite topic, right? So if you think about it, one of the main reasons why asphalt pavements crack and the cost and service life and all of those things is because asphalt binder oxidizes. It oxidizes, becomes very stiff, it becomes very strong, but it also becomes very brittle. Not very much like the aging, unlike the aging process of human beings, right? We also, with age, joints become stiffer and more brittle. So, and if you look at the study of aging, there was a lot of study in Western Research Institute on the chemistry of aging and mechanisms of aging, 1960s and 80s. And then it branched off into these different areas. 1990s, we started looking at what is the kinetics of aging, what is the impact of aging. We also looked through SHARP, like how do you simulate aging in a lab, and what tools do you need in a lab so I can recreate the aging that happens in the field. Both of those valuable pieces of information. But what did it do? It helped us improve our prediction. It helped us improve our specifications. What does that translate into? 10% more life? 5% more life? The real thing that we sort of looked away was the research on antioxidants. That one never progressed, and there was a reason why it didn't progress. But instead of simply predicting how long a pavement will survive, if we had invested that same time and energy into thinking about why can't we stop pavements from aging? Why can't we stop oxidation or significantly reduce oxidation? If we're able to do that, then we're not talking about 10% improvement, we're talking about 100%, 200% improvement, doubling, tripling the life. That should have been our goal, and that should have been the path we pursued, but we didn't. Why? The reason for that was simply because asphalt is too complex a material. It is perhaps the only material it's perhaps the only material in the civil engineering industry where we do not know its exact composition. If you think about steel or cement or concrete, you know exactly what Portland cement is. You know exactly what the molecules are in there, what the chemistry is, and so forth. If you look at steel, you know exactly what steel is made of. Asphalt binder, not so much, because we don't make it. Mother Nature makes it. We just pull it out of the ground, refine it, modify it a little bit. And in the 1990s, until very recently, it was impossible to find out what the chemistry of asphalt binder is, and because if you don't know what it's made up of, you can't fix the problem. You can't stop it from aging. So this is a device I came across in working with another research group on air quality and chemistry. This is really super cool and super expensive. This is like close to $750,000. So by no means is this a specification test or anything, but it is a reflection of not what we should do in asphalt or chemistry. It's a reflection of how far we have come technologically. So this device can really smell molecules in the air in the order of parts per trillion. It's the next best thing to a dog, really. You can use it and train it to detect drugs or whatever, or fruits in your customs or whatever you want to. And even people have used it to detect COVID and so forth. And talking to my colleague, I said, would you please allow me to would you please let me put a bottle of asphalt binder under this and let it sniff? But I cannot make any promises. If this ruins your $250,000 equipment, don't blame me for it. After I made him sign some disclaimers, we stuck asphalt in it, and we've been able to map the DNA of our asphalt binders. These are asphalt binders from different parts of the world, and what you have on the little row that you cannot read at the bottom are different molecules, and how much intensity of those is shown by the color along each row. This was not possible a few years ago. So now today, we have these tools where we can take on a very different journey, and we need to pause, and instead of figuring out how to realistically simulate aging, let's ask different questions. Let's ask, how can we really stop aging and really not get that 10% benefit, but get 100%, 200% benefit? This is really exciting on the things that we can possibly do today. And again, because of the sensors that are in this equipment, because of the computing technology that goes behind those sensors and so forth. So third story is asphalt modifiers. There is a method, it's a very quick and dirty test in the lab you could do. You basically have a little blob of asphalt binder, you melt, you put it, you get a film of this binder, and you run a tension test. It's like any other tension test, except it's done on a film of asphalt binder. But that story is a different story. The thing that we found from that story is we tested hundreds of binders, and we, if I plot all those binders, this is what you see. On the vertical axis, we see strength, it's the tensile strength of a binder. On the horizontal axis, what you see is the ductility of the binder. Anybody who's working with materials would know that if you want to make a good material, you need good strength and you need good ductility. If you don't have ductility, you're making something out of glass. If you don't have strength, you're making something out of, I don't know what's the example, but it's something that will fail or crack very quickly, right? But look at how the dots all line up. All of these are your conventional binders, all of these are the polymer modified binders, and all of these are binders as they age. The beauty about this graph is that, or the interesting thing about this graph is that we did not see any, and we used a lot of modifiers, tire rubber, SBS polymer, this polymer, that polymer, this additive, that additive. There are a lot of polymers in here since this graph was originally produced more. But what we did not find was something in that space that is strong and ductile. I have actually come across additive manufacturers who have figured out things that will put you in that range, put you in that corner, push those points in that corner. Why were those products not really pursued? Because they did not fit our specifications. And why does this line follow that nice trajectory? Because our specifications require it to. We really created goalposts. And so if you're a producer, if you're a manufacturer, if you're a contractor, you would want to meet that goalpost. Even if you think that there is a way to do things better, you're not going to do it because that is not fitting in the specification. You won't get paid to do things better. So that's another area when it comes to materials and modifiers and materials technologies, that there are solutions in that space, but it requires additive manufacturers, polymer producers, agencies, binder producers, and for all of us to come together and say, we need to look at our specifications because we are letting there's a lot of false negatives here, which things that look bad, but they're not really bad. In fact, they push the envelope, make things better. But our specifications, just as they are intended, the specifications are intended to exclude the bad stuff, the things that can cause damage, things that can reduce the life, right? But at the same time, a collateral of that is also tends to exclude things that can improve the service life. So we got to revisit that idea a little bit more broadly. So again, 3 short stories about things in thinking differently about how we can approach materials and pavements and the business that we do as through collaboration between academia, with agencies, with contractors and producers. Not to mention that these are the 3 tracks that are the only possibilities, but these are just stories that fit that theme. Last but not least, a number of you have talked about workforce development. The gentleman right before this was talking about drones and how to excite young people about drones, right? So we also have that problem. Look at that picture. That's a lovely picture. They're looking at an asphalt slab being broken. Has anybody seen so much excitement about failure of an asphalt slab? So this is something we've worked with Oklahoma Asphalt Pavement Association, Professor Zaman, Dominique, folks from OSU, and Texas Asphalt Pavement Association. We created a little asphalt competition for our undergraduates so that they get exposed to the area, they get exposed to the challenges. By the way, that team didn't even win at the end of the competition. But at that moment in time, they thought they're going to win. But I have not seen that much excitement about an asphalt slab failing ever before. and the students, so we started this about 4 or 5 years ago. We've had a break last couple of years because of COVID, last year because of COVID. But the students come back and they say, we didn't even know that pavement and all of this was a profession, like you could do this and this thing even existed. Some of them came back and said that, I didn't know what to do as a civil engineer, what career track to choose as a civil engineer, so they did this. So this was in 2019, the last time we did this in person, perhaps Dominique may be there somewhere, and so we had teams from multiple universities, from Texas, Oklahoma, Louisiana, and we're hoping to do it in person this year, but for sure we're going to do it in person next year. So again, these are ideas where we attract students to the profession with help from Texapa and Oklahoma Asphalt Pavement Association, and it's really been, I'm excited about a lot of research I do, and I have a lot of fun in the lab with, doing all of this stuff with graduate students. But every time I organize this event, it's a different level of excitement. It's a different level of energy. I have not seen DOT. Michael Lee, who was on your advisory board at SPTC, when he found out in 2018 we do this, he called up and said, what's this thing happening? I want to be a judge. I want to be part of it. So I've not seen that much excitement from DOT, contractors, and students all alike. So anyway, those were some ideas, some short stories along those ideas, and I will stop here. This is my last slide. Oh, I'm also should acknowledge DOT, who's funded a lot of these research programs, and the Ergon Fellowship Program, and a lot of researchers. Really, they've said it that we're only as good as our researchers, and there are a lot of people behind this who've done amazing things. So I'll stop here and see if they have any questions. Thank you so much once again for the opportunity.